Hello everyone and thanks to joining me in this presentation. I am Matthias Vara and I work at Huawei Grenoble. This presentation is entitled Verifying the Conformance of a Driver Implementation to the VirtIO Specification. I hope you enjoy it. In a virtualized environment, virtual machines requires to access file system and networking and possible other features. This is done by providing virtual devices that the guest operating system accesses as real devices. For example, network core, disk, serial console. These devices are provided by the virtual machine monitor, which can either emulate them or para-virtualize them. In the second case, the guest operating system has to include dedicated drivers. In this context, VirtIO is a specification for virtual environment that allows the operating system to base on a simple mechanism to communicate with these virtual devices. In other words, it's a standardized way to develop devices and drivers for virtual environment. There are different implementations of the VirtIO devices, for example, in QEMU, RaspVM, or in hardware. Also, there are different implementations of the VirtIO drivers depending on the operating system, for example, Linux, Windows, or bare metal. To develop devices and drivers, engineers have just to follow the specification. VirtIO specifies how devices and drivers must interact. For example, the specification defines how any VirtIO device must be initialized. Let's see more in details the steps that a driver has to follow to initialize a device. To initialize a device, the driver has to follow, say, 6 steps. First, has to reset the device, then it has to set the acknowledge bit. Third, it has to set the driver bit. In the 4 steps, it has to set the feature OK status bit. Then, the driver has to set the driver OK to tell the device that all has been set up. The VirtIO specification specifies the correct order in which the status register must be written. For example, the setting of the driver status bit must precede the feature OK status bit and so on. If we have this information, how we can make sure that our implementation follows the specification to avoid incompatibility problems among different implementations? In this work, we propose to use the formal language CCSL, which stands for the Cloud Constraint Specification Language, to encode requirements from the VirtIO specification. Then, we use the DCCSL specification to validate traces that are generated by the Linux VirtIO driver. In our approach, a verification engineer translates requirements from the VirtIO specification by using CCSL. The main elements of a CCSL specification are clocks and relations. Clocks are used to describe instance of an event. Relations specify how occurrences of different clocks are related. For example, the different steps of the VirtIO specification can be translated into different events, which represent the setting of the different status bits. In this example, I defined 3 clocks which represent the currency of the event driver, feature OK, and driver OK. Then, since these steps must be done one after the other, I use the CCSL relation precede to represent this relation. We use this specification together with the tool named TimeSquare to validate a trace. Validations means to check if a trace violates the specification. In our case, we use the trace generated from ftrace, which allows to trace the execution of the Linux kernel. For example, this is the output of ftrace when we load a VirtIO kernel module. Ftrace outputs the timestamp and the name of the function and the content of the trace print key. We replay the simulation in TimeSquare and the tool informs us when a requirement has been violated. This information can then be used to find potential bugs in the implementation. In the following, I'm going to show you the current implementation of this proof of concept in which I added instrumentation code to the VirtIO driver named VirtIO balloon to generate traces by using ftrace and then validate them by using timescale. What we have here is a modified kernel Linux with some print k to generate the traces. The first step is then to generate the traces by loading a VirtIO kernel module. We load the module and we get the traces. Once we have the traces, we are first going to copy this and put it in a ftrace editor. We just to remove the space. When the file is saved, a trace0.ftrace.extends CCSL is generated. This is the translation of the ftrace into something that can be imported in a CCSL file. This file is imported by the main CCSL file named VirtIO status register for validation. In this line, the trace 0 is imported, and then what we have here is the CCSL translation of the VirtIO requirements. So what we are going to do now is to replay the simulation, and we obtain that none of the traces has violated the CCSL constraint. We are going to try with a different trace called trace 1. This trace has a violation, as we can see here, since feature OK happened after driver OK. We're coming back to the main CCSL file and we import trace 1. Then, when we rerun simulation, timesquare effectively tells us in which steps of the simulation the relation has been violated. For example, the relation feature OK proceed has been violated in step 1 and in step 2. I hope you enjoyed the presentation. You can reproduce this demonstration by following the tutorial, which is in this website. I am going to stay online for QA. Thank you very much.